Welcome to the math record. Today we'll be learning about the paired t-test and its confidence interval. This video will cover chapter 3, part 3 of our statistics class. Okay, a paired t-test. T-test. As I said before in our previous videos, for t-tests there's a one sample, a two sample, and a paired t-test. One sample, you basically just get one sample, and you compare that sample's mean to a mean that's claimed by like some kind of company. It doesn't have to be a company, but it's basically something claimed. A two sample is when you get two samples and you have to compare them to each other. A paired is when you get one sample, but there are multiple elements of it, and you want to compare those elements to each other, basically. So the first thing we do is that we always check the conditions. Okay. First, since it has a paired t-test, you gotta check if the data is paired. So it's paired data. So that's one of the conditions. If it's paired data, the data has to be paired. So you can't get two random samples and then like say it's paired data. It doesn't work that way. I'll show you a example later in the end of what would be considered a paired data. So data is paired. Okay. Next up is that the sample has to be random. As every single other test too, it always has to be random. So the sample is always random. So any individuals added to the sample has to be random, basically. So you can't like just purposely choose some people that might answer a specific answer. Independence. So basically, you can't. Independence is that just because one person like chose this answer doesn't mean like someone else has a different probability depending on the previous person that answered it. So if someone says yes, just because that person says yes, it affected another person's, which is not true. So they're independent of each other. So individuals are independent, basically, are independent. IND. I'm not gonna write out the entire thing. And then you have the 10% condition. The 10% condition is that your sample size n, which stands for your sample size, is less than 10% of the population that you're basically studying. So if you have you're studying 10 students from your high school, that means there must be 100. There must be over 100 students in your high school, basically, for you to take 10 people in your sample. So for a 10% condition, you don't need this. So this is not needed. This is not needed if your sample is random, basically. So if it's like a SRS, it's a simple random sample, basically, then it's gonna be fine. So it's not needed if it's a randomized experiment, like a randomized experiment, basically. But it's good to have if you want to. It's not needed, but it's optional basically. But you don't have to do it. Okay. Let me delete this. I'm running out of space. And the last one you have to check is the nearly normal condition, which is the same thing with one sample and two sample t-tests, which basically your histogram has to be normal. So, as I said before in like my other cases, if you make a histogram, right, your data makes a histogram, then basically this histogram has to be normal, like so it has to be like unimodal or somewhat unimodal, basically, because this seems like there's another peak right here. But since these are so close to each other, basically you could just say that it's unimodal approximately. And it has to be symmetric, so this side has to be similar to this side or somewhat approximately similar. You could also bypass the nearly normal condition and say the histogram is nearly normal. You have to write down that the histogram is nearly normal, basically. If your sample size, your n, right, is greater is equal to 40 or more or 30 or more. I use 40 because that's just a general number that I like to use. But 30 is fine if you want. Okay. So basically, after this, you do your transition. After you do all your conditions, and you do the histogram, and you draw out your histogram and say it's nearly normal. You do your transition statement, which is basically the same as every single other transition statement. So you say, since the conditions are met, the ones that you just checked the conditions are met, I can construct a paired t-test. So it's basically a t-test, but paired. So it gets from one sample, and there's multiple elements in that sample that you have to compare, and you have, or is it like just basically two elements that you have to compare? And it has to do with means, so it's not proportions. You have the transition statement, okay? And now you actually do the test. So your test is your null hypothesis, HO, is the U, and then you put subcreate diff, which stands for difference, is equal to 0, because there's multiple elements. So element 1 minus element 2 has to be equal to 0. So if that happens, you just call it a U difference, basically. Alternate hypothesis HA, you say your U difference is you either say it's greater than 0, less than 0, or it's not equal to 0. So those are just the basically 3 cases. Based on what your question is asking, you're just gonna use one of these. So less than, greater than would be like if it's like right here. Less than would be like if it's right here. And if it's not equal to, basically both sides. Similar to how all the other testers are doing it. Not equal to is both sides. Greater than is to the right side, and less than is to the left side. So that's the test. Now you have to define your variables. As I said, always for a bunch of these tests, you don't have to define your variables all the time, but it's good to have. So your U difference, your U diff, is equal to your mean difference is equal to the mean. Is basically defined as the mean difference, and of basically the actual mean difference of the thing. So you have to put it in context. So I'll explain this later once we use our example, because it makes more sense. Oh, sorry, I don't know why I'm erasing this, but okay. And you could define your standard deviation you want, but basically that's all you need to define. And then you have like other things you could define also, but yet that's more based on context than anything else. Okay. This would be shown in the example. I'm sorry that I'm being vague right now, but it's kind of is because of the pair t-test and how it's set up. Okay, the mechanics, which is basically all the math portion. Basically, your mean. Since you said your mean difference is 0, that means your mean is 0, basically. And your standard error is equal to the standard deviation of the difference. The difference standard deviation, basically, and then you put a square root on it. Square root over n. Basically, that's your standard error. And your t-score, right, is equal to your mean difference, so your U diff, divided by your standard error with a degree of freedom of the number of pair. Basically, you're gonna have you have one sample, right? But you're gonna have like multiple elements, so it's basically just the number of pairs minus 1. Okay, so you have 3 pairs, then your degrees of freedom is 2, because 3 minus 1 is 2. And then you always write your alpha level, which is usually 0.05, unless they ask you to use a different one, like 10%, then it's 0.1. And then you make a picture, basically. So you say your zero is right here, your mean, your standard error is right here, and you say like your U diff is right here. So you want to have something like right here, basically. So you draw a picture. I'm just giving an example. It doesn't always look like this. So after you do your test and you get your p-value, which is you do your conclusion. So if your p-value is less than 0.05, which is your alpha level, you reject the null hypothesis. You reject the null hypothesis, and you say the alternative hypothesis is true. And if your p-value is greater than 0.05, you fail to reject the null hypothesis. Fail to reject. I'll just erase this part. Fail to reject. Okay? The null hypothesis. And you say the alternative hypothesis is false, basically. But you have to write this in context and in words. So you say based on your p-value of whatever your p-value is, which is, let's say if your p-value is less than your alpha level, which is 0.05, I reject the null hypothesis, and then you basically put a comma and write your null hypothesis, and say there is evidence to suggest the alternative hypothesis is true, and then write your alternative hypothesis. You have to do everything in context. So explain what your null hypothesis is. Explain what your alternative hypothesis is. And if your p-value is greater than 0.05, you say, since based on my p-value of whatever your p-value is, which is greater than 0.05, I fail to reject the null hypothesis. Talk about your null hypothesis. And then there lack evidence to suggest your alternative hypothesis, and then explain your alternative hypothesis is true, basically. So you say there isn't enough evidence that the alternative hypothesis is true, and you fail to reject the HO. So you did not reject HO, basically, the null hypothesis. Okay. And then after your test, if you want to follow up with a confidence interval, you basically can follow it up. So confidence interval. Because usually after a test, they're going to ask you to follow up with a confidence interval to say where the true difference between these elements are. And your mean is now your the mean of the difference. And your standard error is basically your standard deviation of the difference. So the difference standard deviation. So you subtract if you have two elements, you subtract element 1 by element 2, and then you find all those elements, and then you find the standard deviation of that, basically. And then you divide that by square root n, right? Square root of the sample size. And then to find the interval is basically just the mean, plus or minus the t-score, with a degrees of freedom, always with a t-score. Models for 1 sample, 2 sample, or 3 samples, you have a degrees of freedom. The 2 samples is weird. The 1 sample is basically the amount of the sample size minus 1. For paired, it's basically the same thing. It's just basically with pairs, so degrees of freedom of the number of pairs basically minus 1. So you have 3 pairs, you have a degree of freedom of 2. And then you multiply that t-score by its standard error, which is this number right here that you're going to have to calculate. And after you do that, you basically write, I'm something percent confident. You don't know what percentage, so let's say 95%. I'm 95% confident that the true mean difference between whatever that you're doing is within the interval, and then you talk about your interval, basically. And that's the confidence interval. Now let's actually work with an example. So we have this chart. So the table below right here shows 40 out of 1,000 students across the country that took the SAT. So there is each of these is a pair, so it's one student. So basically this will count as one student right here, right? So this is one student, this is another student, this is another student, right? And then there's 40 of them. So there's 40 students. Is there a significant difference between the math and reading and writing SAT scores? So the first column is the math. So this is the math, this is the math, this is the math, and this is the math. And this is the reading and writing together. This is the reading and writing. This is the reading and writing. And this is the reading and writing combined together. So like how you read this is that student 1 got 700 in math and 560 on reading. Student 2 got like 620 in math and like 690 in reading, and etc. You basically read the rest. So that's 40 students each. So basically there's 40 students, but there are multiple elements. One for math and one for reading and writing together, right? So you take your calculator. I use the Nspire, so I'm just going to tell you how to do it on the Nspire. Go to your spreadsheet, make a spreadsheet, and then label your first column X, and label your column A X and column B Y. You could call it math or math and the other math A, and then B as reading and writing. But X and Y should be fine. It doesn't really matter. And then for X, just plug in all your math ones. So you put a 700, a 620. You have to put this in the right order. So 700, 620, 560, 800, a 590, a 640, a 560, a 600, and then a 760, a 630, and then the next one is a 690, all the way up here, right? So a 700, a 550, and then you basically write the rest. 540, 540, two 720s, a 770, 630, a 560, 650, a 800, a 720, a 680, 700, 780, 710, 50, 80, 20. Sorry if this is taking a little long. I'm doing this like right beside you also. So I'm doing this just right now. 75, 70, 50, 660. And once you get all your math in there, which should be 40 scores, now you're gonna put in your reading. So put it under your Y or under your reading and writing column. So it will be 650, 690. You have to keep it in this order though. You have to keep all this in this order because like you can't put like 700 together with 690 like for the first number because the first student got a 700 in math and 560 and 90, and this is why it's called paired data because like one student basically got these numbers and you see why it's paired basically because it's that one student that got it in that one score basically. And you want to test if there's a difference between math and reading for these students, and this is why this is paired data. Okay, so the reason why you can't use two samples as a paired is because it's like let's say they took 40 from one sample and 40 from another sample. Those 40 are not the same as each other. So just because like let's say you took one from a male a sample, one from a female sample, just because a male got like a score of like 400 doesn't mean a female is gonna get a score of 400, you know? It's not correlated. But these are correlated because basically one student got a math score and then a reading score, another student got math and a reading score. You see how they're paired? Because they're related to each other because one student did that score. So I'll put in the rest of these scores. Okay. The worst thing about putting things in tables is that if you mistype it, then you're gonna get the answer is wrong. Because instead of like saying you didn't put like 410, you put 140. So that's sometimes bad. So sometimes you might want to double check your table to make sure they're right. So 740, 650, 480. And now in the last column. Okay. And then we can finally do the math on this. 770. Sorry if this is taking a while because I'm plugging this into my calculator. 50, 680, and a 800. Okay. So basically, you got these two columns. Your column A is your math. Your column Y is your reading and writing. Now you're gonna go to column C, and then basically you're gonna title this as like diff, so difference or something. And then you're basically gonna go to the column right below it. So there's two blue columns. The first column is what you name it. The second column is your formula. So press enter on that column, and it says your basically whatever you name it, a colon is equal to something. So if you're using an Inspire, you press your var button and press X, and then press enter. Right, go down to the X, and then you press some minus var button again, and then press your Y. So basically, this will get you your entire. You don't have to do other calculations. This function would basically do all your calculations. So it'll be like your difference is equal to your variable x minus your variable y, because that's your what you title as your first column, your second column. It's what I title it. You title it whatever you want. So basically, you whatever you titled it, you have to put those as your variables. So it'll be so what it will be counting is like 700 minus a 560. So your first number is 700 minus 560 is 140. 620 minus 690 is negative 70, and it does this for all the 40 numbers, basically. Right? Now press on your Inspire, and then go to the one to the right of it, which is the stat data and statistics, the purple icon. Press enter, and then go to the bottom. Click to add variable, not the left one, the bottom one, and then press the difference one. All right, okay, and then press menu, and then press plot type, and then press histogram. So based on this number, we're gonna have to see if like this is like a normal model, basically. So when we drew this, let's draw this out. So this is a little strange because I have a bunch of numbers. So it's something like this. Oops, sorry, a little too big. And then it has something all the way up here, and then it has 3 numbers with a gap, and then another gap with 2 numbers, and a really big number right here. Smaller one, a little bit bigger, that's smaller, and then about the same size right here. And then it has 2 of them. Okay. So it has something like this, which doesn't really look that unimodal. But I mean, this normal model, and this is why like you always have to check the nearly normal condition, because you could just while this is not nearly normal, we could just say it's kind of somewhat nearly normal. So if you just say it, then basically you just if you just say it's somewhat near normal, not saying it's nearly normal, say it's somewhat nearly normal as your condition. You could say it's kind of unimodal, because I'm sorry that the graph looks bad, but this is actually the biggest one, and there's actually multiple peaks. Like there's one here, there's one here, there's one here, there's one here, and there's one here, there's one here, and there's one here, right? So there's like 2, 4, 6, 7. There's like 7 peaks, except for like this one is kind of like debatable. This is debatable, and this is debatable, basically. So technically, there's like 4 to 7 peaks, but you could just say it's about unimodal. And then you say this side is somewhat symmetric to this side, so you could say it's approximately somewhat approximately normal. So while your test is not the best, it could work somewhat. So it'll give you a general idea, even though it's not like the best test to do, because there's nothing else you could do about it. So just do a test on this. See, even though it's not a good like idea to basically use a test on this because it's not a normal model, you can still use a test on it. It's just that you're not gonna be as certain about your answer, but you can still do it. So based on this, let's do our conditions. So our conditions is we already checked the nearly normal, so we need to check that it's paired. So is it paired? Yes, it is paired. Each student has a math and reading score. Each student has a math and reading and writing SAT score. Right? So it's paired. Put everything in context. The sample is random, which is true because based on the question which I said earlier, we took 40 students 40 random students, right, from thousands, basically, of students across the country. Okay, and independence. Say each student score is independent of each other. So students' scores are independent. Are independent. Independent. So just because someone got an 800 on a test doesn't mean someone else is likely to get an 800, basically. I'm starting around in space, I'll just write here. 10% condition. So your 10%, your sample size of 40 has to be less than the 10% of the of all the students that took the SAT in across the country. I said thousands, so 10% of this should be like 400. So 1,000 is obviously higher than 40, so this works. So this checks all the conditions, except somewhat the nearly normal condition, which you have to draw the model and explain that it's kind of unimodal and is somewhat symmetric. So you could say the nearly normal. Then you draw the picture. You draw the picture of the histogram and say it's the histogram is a somewhat approximately normal. So while it's not the best graph, you could proceed with caution. Basically, that's what you say, and then you write your transition. I'm just gonna say out loud. I'm not gonna write it. Since the conditions are met, I can construct a paired t-test. So whatever I wrote before in the beginning of the video, basically that's what you write. Okay. You always just write since the conditions are met. You always write that part and say I can construct a whatever test you're gonna do. So in this case, you do a paired t-test. If you're doing a two sample, just say two sample t-test. So you just always use that transition statement. So you could tell them which test you're using. And now you're gonna do your test, which is your null hypothesis is that your the mean difference between the math. So because you had x minus your column was x and your column was y, which I named it as x minus y. Your x is your math, your y is your reading and writing. So it'll be your difference between the math and the reading and writing. So I'll just put m minus r. So math minus reading. I'm not gonna put writing. Who cares? So let's put is equal to 0, right? The mean, and then the mean average for a is we say the u of the m minus r. So we have to ask, what's the question again that we were asking? The question that we asked was, is there a significant difference between math and reading and writing? So it says a significant difference. So is math bigger than is math unusually bigger than reading, or is reading unusually bigger than math, right? So basically, it's not greater than or less than. It's both of them. So it's not equal to, right? So this is gonna be a two-sided, basically. So you're gonna have something like this, right? And you're gonna have, if you find something here, then basically you multiply this by 2 because it's symmetric on both sides and you have to get both these areas, basically. Even though the picture's bad. So something like that. And you now define your variables. You say your m minus r is the mean difference between students' math and reading and writing SAT, basically. And that's basically all you have to find. If you want to cite your sample size, you say n is equal to sample size of basically 40, because you have 40 students. But it's not 80 because it's 40 because it's just 40 students had math and reading. 80 would be the amount of like scores. There's 40 math and 40 reading, so it's a total of 80. But there's 40 pairs basically. So you have n is equal to 40. So you have 40 pairs of math and reading, right? So, sorry, my it's not working right now. Math and reading, right? So you define your variables. Okay, now let's actually move on to the math, the mechanics. Okay. So for your mechanics, your mean, as I said before, is 0. Your standard error is equal to your standard deviation of the difference of this thing. So you're going to go to your calculator, your ends bar. Go back to your spreadsheet where you have all those numbers, right? And then go to an open, basically white rectangle, not the blue one, the white one. And then press menu. Go down to data, which is number 3, and then go down to list math, which is number 6. And then press go to number 7, which is sample standard deviation. Press that. And then right here you press var, and then you press your diff, not the math, the x or y, which I named it as. Press the standard deviation sample of the difference, and you should have a sample deviation difference of 139 point about 139.4, right? Approximately, and then you square root over the square root of the sample size, which is 40, because we have 40 pairs. So let's do the math on this. So you have 139.4 divided by square root of 40, and you get approximately equal to 22.04 ish, rounded basically. And then now you have your t-score, which is basically your U difference, your mean difference. So go back to your spreadsheet and go to a different white rectangle, and then you press menu again, go to data again, go to list math. Now you press mean, number 3, and then var, and then basically the difference mean. So which is okay, which is 78.75. Okay, so that's your mean difference. So this is telling me that the math score is usually bigger than your reading score. Yeah, and you have a standard error of 22.04. So your t-score is this number divided by your standard error, which is 22.04. So using that number, so 78.75 divided by 22.04, it's approximately equal to 3.57. And your degrees of with a degree of freedom, remember, a degree of freedom is equal to the number of pairs minus 1. So you have 40 pairs. 40 pairs minus 1 is 39, with degrees of freedom of 39. Right? And then your alpha level, always write your alpha level, is 0.05, which is usually the case 0.05, unless they choose a different number. So we're going to use 0.05. And now we're going to make a picture. Okay? So, yeah, something. Sorry, this is a T model, so it's like more splattered out than a Z. So something like this. Let me redraw this. Okay. Something like this. Okay. You have a mean of 0. Because you expect it to be 0 if they're equal to each other, if there's no difference. So mean, the math minus the reading is 0. And then you have a standard deviation of 22.04. And your original number was 78.75. So it's somewhere like right here, because it's like 3.5 standard deviations more, about. So 78.75. Right? You have to remember your alternative hypothesis. So your alternative hypothesis was not equal to, so it had to be both sides. Remember when I said that? So it's something right here, and you have something right here, which is negative 78.75. This is the negative version because they're basically symmetric. So you have to put it right here. So it's both of these areas. So whatever you find the area right here, basically just multiply by 2 and you get the entire area. Okay. So let's find the p-value. Go to your calculator. Right? Get out your spreadsheet, go to A, which is calculate. Press menu, go to probability or statistics, doesn't matter. Then go down to distribution, and then press TCDF, right? So your lower bound, since you're gonna do this one right here, your lower bound is your 78.75, right? So it's gonna be this number, your t-score, because you're gonna put your t-score in. So you gotta put your lower bound is 3.57. And your upper bound is that if it gets really, really big, it's just a really big positive, right? So you just put 9, the capital E 999. Don't put the actual lowercase e. That means that's a different number. It's basically an exponential number. Put the actual e that it looks like this, 9e999, right? Put a really big number. You can put like 1,000, 2,000, doesn't matter. Just put like a really big number. And your degrees of freedom is 39. Press enter. And you get your p-value is equal to 0.000483, etc. But since that's only for this area, you have to get this area also, so you multiply by 2, right? As I said before. So your p-value is actually 0.00097-ish, right? So that's your p-value. So this p-value is obviously smaller than 0.05. So you're gonna reject the null hypothesis because there is a difference between the math SAT score and the reading SAT. So you say, so based on that, your conclusion, based on the p-value of 0.00097, I think, whatever that number was. Whatever that number was, I'm sorry if it's a different number, but I think it was this. Is which is less than the alpha level of 0.05, right? Because that was your alpha level. I reject the null hypothesis, right? And you say the alternative hypothesis is basically true. But you have to put this in context. Don't write this one out. It's just because I'm running out of space right here. So you write based on my p-value of 0.00097, which is less than the alpha level of 0.05. I reject the null hypothesis that the mean difference between the math SAT score and the reading SAT score is 0. There is, and then you say your second sentence is that there is evidence to suggest that the alternative hypothesis that the math score that there is a significant difference between the math score and the reading score is true. So basically, your two sentences say in that context is that your that there lack that there is evidence to say that that the math score and the reading score is uneven. So it's either that the math score is bigger than your reading, or your reading is bigger than your math. And you're saying there's evidence. You're not 100% sure, but there is evidence. Okay, it's just that it's very unlikely. It's very unlikely that that they would have the same score because the p-value is so low. Like it's not even 1%. It's like 0.9 of a percent ish, or 0.1 of a percent if you round this up to like the next number right here. So that's your conclusion. Now, if they ask you to follow it up with the confidence interval, right? To say where is the true difference between your math and reading score is. So what's the true difference between those scores? Okay. So now your confidence interval, your mean is now equal to your the mean difference, which we calculated before, right? Which was going back to your spreadsheet to find your the mean. So don't ever delete your spreadsheet. If you delete it, you're gonna have to redo the work all over again. So your mean was 78.75, right? Of the difference between the math and reading. So this is the math minus the reading. It's not the reading minus the math, okay? So make sure you're correct about this. And then you're gonna have a standard error, which is basically your standard deviation of your difference, of the difference divided by the square root of your sample size, which is n, of the number of pairs, basically. So you have your number, right, which was 139.4. Remember we did this already? It's basically the same thing. So 139.4 divided by square root of 40, right? Which is approximately equal to like 22.04. Remember this number? Now you're gonna have and your degrees of freedom, remember, was 39. So we're gonna remember that. So we have to put that for the t-score. So it was now you have a t-score. So if you want to find an area of 95, right? As I said as I said in my previous videos, if you could do a inverse area, basically, where you're gonna what the calculator does is that it finds the area from here all the way up to that point. So if you want a 95% area, this will count as the 95, right? When what you really want is like right here. You want this area to be the 95, not including this area, which they're adding in. So what you have to do is that you're gonna have to find that area, that basically up to that point for this area up here, basically. So if you want to find a 95% area, right? Basically, this area is 95. So since it's symmetric on both sides, this has to be 2.5, and this has to be 2.5, plus 2.5 plus 2.5 is 5, and 2.5 is equal to 2.5. And 5 plus the 95 is 100. So it's 2.5 plus 95, which is 97.5. So you have to look for an area that's 97.5 on your calculator. For the Inspire, I'm not sure about the TI-84 or any of the other ones. So go to your calculator, go to menu, go down to probability statistics, doesn't matter. Then go down to your distributions, and then go down to inverse t, which is number 6. And then your area is 0.975, right as a decimal, so it's 0.975. And the degrees of freedom is 39, because you have 40 pairs minus 1 is 39, right? And you get a t-score of about 2.02. So your interval is basically just your mean, 78.75, plus or minus your t-score of that degrees of freedom. So t-score of 22.02 times your standard error, which is 22.04, right? So you have 78.75 plus 2.02 times 22.04, and 78.75 minus 2.02 times 22.04. And you should get two numbers, which is approximately 34.23 and 123.27, right? And you can also use your confidence interval to help you answer your hypothesis test. So your original hypothesis test was asking, is there a difference between the math and reading score? So if there's no difference between a math and reading score, that means there should be possible a 0 be between this. Because if the math and reading is the same, then basically they subtract each other, they should be 0. But since 0 is outside of this interval, so it's below the 34 because both of them are positive, then that tells me that because these numbers are positive, which is your math minus your reading, that means your math is higher than your reading generally. So so basically on your confidence interval, what you write is that I'm 95% confident because you use the 95% area. I'm 95% confident that the true mean difference between um, the math SAT score and the reading and writing SAT combined SAT score is within the interval 34.23 and 121.27 points. Or you could basically write, I'm 95% confident that the mean math SAT score is 300 and is 34.23 to 123.27 points greater than the the reading and writing combined SAT score. You just have to understand what the variables are standing, and you basically just write a confidence interval, explain that's a 95%, and explain the interval. And those are the ones that you have to write. Okay? So that's basically if you do everything by hand. If you're using an Inspire like me, then basically if you don't want to do any of the work, all you do is that you go to your calculator, right? Press menu. You're gonna have to do your you have at least you have to put in everything for your table. So you have to put in your math scores and you have to put in your reading score, and you have to find you have to make the histogram. Yet if you uh The only part that you use for your calculator is that you don't want to do the mechanics. You could just write down the numbers, but you don't have to do the math yourself. So what you do is you go to you do the do at least the data and statistics, which is write the table, get your mean and standard deviation, and you get your histogram, and you say it's approximately normal. So you check all your conditions, and you write your hypothesis test. This is only just so you don't have to do the math. So the statistic goes down to your statistics, goes down to your stats, go down to your calculator, go down to statistics, which is number 6, then go down to number 7, which is your stats test, and then you're gonna do a you're gonna basically gonna do a t-test, but you basically have to do so your t-test is basically gonna be your same thing as you're gonna be your paired, right? So what you have to do the math. It's similar to a one sample t-test, but now you just got to plug in a paired kind of version. So t-test, press t-test, then go down to stats, not data input method is stats, not data, and press OK. So your mean difference is 0, and your mean of your sample is the x. So the mean of the sample, go back to your spreadsheet to find out what it is. Your spreadsheet, it says that your mean was you probably want to write this out, so let's just write it out right here. So Control C. Okay. So remember our mean is gonna be 78.75, and our standard deviation is gonna be equal to 139.4. Okay. So we just gotta plug this in. So calculate, go back to menu, go back to statistics, go back to stats test, go to your t-test, input method stats, data input method stats, okay. Your UO is 0, because you expect the mean difference to be 0. The mean of your sample is 78.75, right? Your standard deviation is 139.4. And your N is 40, because there's 40 pairs. And your alternative hypothesis was your U is not equal to your UO, right? So press OK. And now you basically get everything. So your t-score is equal to 3.57, so it's pretty similar to what we got. Our p-value is 0.0096, which is really close to what we got, which is 0.0097. So it's just not that much of a difference, so it's fine. Degrees of freedom is 39. Your mean is 78.75, and your standard deviation is 109.4, which is what we put down. And your n is 40 because you have 40 pairs, right? So this, based on your p-value, which is 0.0096 from your calculator, which is basically just rounded because you didn't put in the precise numbers. You basically just rounded your standard deviation. So so that's why. And then basically that's for your stats test. So if you have a p-value of 0.0096, which is less than the alpha level of 0.05, you just use that to fail to reject. So you don't have to do all the math. So you could bypass like the entire mechanics if you want. And then if you want to get the confidence interval, go to menu again, go to statistics number 6, go to confidence interval number 6, and go to t interval, so number 2. Data input method is stats all the time. Always use stats. The mean was 78.75, right? Our standard deviation is 139.4, and our n was 40. And we want a 95% confidence interval. So press OK. So we have a interval of 31.17 to 123.33. So which is similar to what we got as our interval. So it's just about slight differences because the calculator is more precise while we are doing a lot of rounding, basically. And that's basically how you do the pair t-test. So in this video, we basically covered the pair t-test and its confidence interval. Thanks for watching, and I'll see you at the next math record.